Okay, welcome once again. Today we are going to be looking at oxidation and reduction. Typically we call it redox or redox reaction, redox equation, as the case may be. So oxidation and reduction is what we're going to be looking at. And I remain your teacher, your tutor, Anjorin Oluwafemi Excel, and I'll be taking you through this lesson. And please, I want to ask for your undivided attention as we proceed in this class today. All right, let's jump in by looking at the learning objective for this particular topic. By the end of this lesson, students should be able to, number one, define oxidation and reduction in terms of electron transfer, addition, removal of oxygen and hydrogen, and changes in oxidation number. So this is the first thing that you should be able to do by the end of this lesson. Secondly, you should be able to identify oxidizing and reducing agents in chemical reactions. And then thirdly, you should be able to assign oxidation numbers to elements in compounds and reactions using standard rules. And we're going to be going through those rules as we go along in this lesson. Okay. And fourthly, you're supposed to be able to differentiate between redox and non-redox reaction using changes in oxidation states. And you're also expected to be able to balance redox reactions in acidic and basic media using half reaction and oxidation number method. Okay. You're also supposed to be able to apply high-pack naming based on oxidation states to write correct compound names and demonstrate simple tests for identifying oxidizing and reducing agents in the laboratory. All right, let's go into the core of the lesson now. Oxidation and reduction, which we refer to as redox. Okay. An oxidation reduction reaction is a type of chemical reaction that involves a transfer of electrons between two species. An oxidation reduction reaction is a type of chemical reaction that involves a transfer of electron between two species. So we have established that now. Two species, there'll be a transfer of electrons between them. One is being oxidized, the other one is being reduced, and vice versa like that. Okay. An oxidation reduction reaction is any chemical reaction in which the oxidation number of a molecule, atom, or ion changes by gaining or losing electron. So the oxidation number will change by gaining or losing electrons. So we refer to that as an oxidation reduction reaction. Okay. So redox reactions are common and vital to some of the basic functions of life. Example, photosynthesis is an example of a redox reaction in which there's a loss and a gain of electron, for the photosynthetic process to be able to take place. Respiration is another basic life function that involves redox reaction. Combustion and then corrosion or rusting is another life, basic functions of life that involves oxidation reduction. All right. All right. Let's move on now and go to the next one. Definition of oxidation and reduction. Now we want to define based on certain terms or based on certain, concepts, so to speak. So the first term that I want to define oxidation and reduction is in terms of oxygen and hydrogen. In terms of oxygen and hydrogen, how do we define oxidation and reduction? Now, oxidation is the addition of oxygen to a substance or the removal of hydrogen. That is the definition of oxidation based on oxygen and hydrogen addition or removal, as the case may be. So oxidation is simply the addition of oxygen to a substance, and it is the removal of hydrogen from a substance. Okay, all right now. Okay, so reduction, on the other hand, is the removal of oxygen from a substance or the addition of hydrogen to a substance. So that's reduction. That's definition of oxidation and reduction in terms of oxygen and hydrogen. Okay, let's look at some examples now. Oxidation, addition of oxygen. When you add oxygen to carbon, you have carbon dioxide. That's an oxidation reaction that has taken place there. Okay. The second one is reduction, which is removal of oxygen. You have CuO plus H2, and then the copper is being reduced, and then hydrogen gets the oxygen, is oxidized. So that's the removal of oxygen from copper, and it reduces copper to its elements. Okay. So that's in terms of oxygen and hydrogen now. Now oxidation. We still want to look at oxidation in terms of removal of hydrogen now. We have looked at this in terms of addition of oxygen or the removal of oxygen. So in terms of removal of hydrogen, oxidation can be referred to as the removal of hydrogen, like we said. When you have H2S, hydrogen sulfide reacting with chlorine, you discover that the hydrogen is being reduced. So the sulfur is oxidized, and then the chlorine becomes reduced in the process. So that's oxidation in terms of removal of hydrogen. Reduction in terms of addition of hydrogen, we can see with ammonia, the formation of ammonia, where we had hydrogen to nitrogen to give us that. So that's reduction in terms of addition of hydrogen. Okay, all right, now let's take it a notch further. Let's look at another one, still looking at definition of oxidation and reduction, but this time around, in terms of electron transfer. Now, in terms of electron transfer, we say oxidation is the loss of electrons. Oxidation is the loss of electrons. Reduction is the gain of electrons. Oxidation is the loss of electrons. Reduction is the gain of electrons. Okay. Now, there's a particular mnemonics that is very, very useful. I used it while I was in school, and I think it's very, very simple. It helps us to be able to understand this concept perfectly. When you use the mnemonics oil rig, and Nigeria is blessed with oil, so we can easily relate now. Oil rig, oil rig. Oxidation is loss. That represents oil, Abi. Then rig, reduction is gain. So if you want to define oxidation and reduction in terms of electron transfer, and you don't want to stress your brain at all, just remember oil rig and say oxidation is loss of electron, reduction is gain of electron. Shikena, so that's all. Like the Hausas will say. And so so just remember the mnemonics, and it will be of great benefits to you. Example from this particular definition, when you have this is an oxidation because electron is lost. Sodium loses its electron, and it becomes oxidized in the process. You can see that with chlorine, it's not like that. It gains electrons and becomes reduced in that regard. So that's a very good example. So that's oxidation and reduction in terms of electron transfer, and also in terms of oxygen addition and hydrogen remover. So we want to consider oxidation number now. We want to look at oxidation number, and we want to look at oxidation number. So let's dive in. There are certain rules that we must understand for us to be able to or comprehend how to calculate oxidation number and the oxidation state of elements, either in a compound and so on and so forth. So these rules, we are going to look at them one after the other, and then we try as much as possible to master them so that we can apply them. Okay, the first one is, okay, before we go into the rules now, let's go through this, like the intro into the rules that will come forth one after the other. The oxidation state of an element corresponds to the number of electrons that an atom loses, gains, or appears to use when joining with other atoms in compounds. Okay. In determining the oxidation state of an atom, there are 7 guidelines to follow. So for us to determine the oxidation state of an atom, we must follow 7 guidelines. The first one says that oxidation state of an individual atom is 0. So when we have sodium, an individual atom, unbonded, uncombined with any other atoms or elements, the oxidation state of that sodium is what is 0, because it's an individual atom. Okay. The second one says that the total oxidation state of all atoms in a neutral species is 0, and in an ion is equal to the ion charge. Now, let me make it clear and just lay it bare for you. Now, when you have let's say an atom like a neutral atom, like maybe let's say like we have sodium chloride. Let's say sodium chloride. Now, the total oxidation state of all atoms that form sodium chloride, sodium and chlorine are the atoms that comes together to form sodium chloride. The total oxidation state of all the atoms is equal to zero. Why is it zero? Sodium chloride is a neutral species, so it will be equal to zero. But that is not the case when you have a charged species, either positively or negatively charged. I'll give you an example. If you have SO4 2 minus, SO4 2 minus, that's superscript 2 minus, I mean now. What you notice is that the oxidation state of all the atoms, which is sulfur and oxygen, will be equal to -2. That is the overall charge on that particular compound or atom, as the case may be. So we say it is SO4 2 minus. So it is sulfur plus oxygen, which will be equal to -2. So it is a bit different. So it will be equal to the overall charge. But for a neutral atom like sodium chloride, it is just equal to 0. And that is what guideline number 2 is talking about. Now, group 1 metals have an oxidation state of +1, and group 2 have an oxidation state of +2. It's the fundamental rule. Most of the time, it checks out with a little exception anyway, but most of the time, this is fundamental. This is crystal, it does not really change, So metals in group 1 +1, metals in group 2, they have oxidation states of +2. Guideline number 4 says that the oxidation state of fluorine is -1 in compounds. Yes, this is also fundamental. Okay. The fifth one says that hydrogen generally has an oxidation state of +1 in compounds, but there's always a variation to this rule when you have hydrogen in hydrides or something like that. So please, let's take note of this. But generally, hydrogen has an oxidation of +1. It's oxidation state of +1 in compounds. So we need to take note of that. Then the sixth one says that oxygen generally has an oxidation state of -2 in compound, but you can check out for peroxide and see if this actually works out, but generally oxygen has an oxidation state of -2. So please let's be mindful of this. Now, in binary compounds, group 17 elements have an oxidation state of -1. Group 17 elements refer to the halogen family: fluorine, chlorine, and so on and so forth. Those ones are the group 7 or group 17 elements. They generally have an oxidation state of -1, whereas group 16 elements, I think that should be the sulfur group, if I'm correct now. It has oxidation, it's group 16 elements of -2, and then group 15 element, that should be the phosphorus group of -3. So these are the general oxidation state for all those groups on the periodic table. So we should be mindful of that, and we should take note of these 7 guidelines that will help us a lot as we go along. Now, the sum of the oxidation states is equal to 0 for neutral compounds. I've said this before when I was talking about the guideline number 2, and equal to the charge for polyatomic ion species, CO3 to CO3, 2 minus, SO4 2 minus, and so on and so forth like that. So it's equal to the overall charge on the polyatomic ion. So let's be mindful of these guidelines, and we'll be fine if we are mindful of them. Okay, let's push now and move to the next thing. Assigning oxidation states is the next thing that we need to look at or consider. So let's look at this example. It said, determine the oxidation state of each element in the following reaction. This is so iron moving plus oxygen to give us Fe2O3, okay? Fe2O3. And then the second one is just iron with a charge of 2 plus, in aqueous solute, in an aqueous is aqueous, so it's in solution. And then this is silver reacting with hydrogen sulfide to give us silver sulfide and hydrogen. So we have to determine the oxidation state of each element in the following reaction. So how can we go about solving it? Now, for the first one, which is for the iron and oxygen are free elements. Therefore, they each have an oxidation state of 0 according to rule number 1. The product has a total oxidation state equal to 0. And following rule number 16, Oxygen has an oxidation state of -2, which means iron has an oxidation state of +3. Okay, that's good. So the second one, the oxidation state of iron just correspond to its charge. Since it is a single element species, therefore, the oxidation state is +2, equal to the overall charge on it. Okay. For the third one, silver has an oxidation state of 0 because it is a neutral species. Hydrogen has an oxidation state of +1, according to rule number 5. Hydrogen molecule has an oxidation state of 0. Okay. And sulfur has an oxidation state of -2, according to rule number 7. And hence, silver in Ag2S has an oxidation state of +1. Okay, all right. So that's how we figure or determine the oxidation state of elements. All right, let's push it a bit further and look at my still assigning oxidation state, example 2 now. Determine the oxidation state of phosphorus atom. Phosphorus atom elements in each of the following species. Okay, I think it was trying to say that maybe the element that are in bold is something like that. They are bolded or something, or in bold, that they are captioned in bold, so to speak. I think that's what the question is saying, but there's a little mix up. But what we're just trying to do is just determine the oxidation state of phosphorus atom. So what is the oxidation state of phosphorus atom in Na3PO3? That's the first one. The second one is what is the oxidation state of phosphorus atom in H2PO4 minus? And then if you look at it, let's solve it together. The oxidation number of sodium and oxygen are +1 and -2. Because sodium phosphide is a neutral species, the sum of the oxidation numbers must be 0. Letting hence be the oxidation number of phosphorus. That means 0 will be equal to what? 3 multiplied by +1, which is from sodium, plus X, which is the phosphorus that is unknown, plus 3 into -2, which is from oxygen. So the oxidation state or oxidation number of phosphorus in that particular compound is +3. Okay, hope that is clear. Hope we got the concept. It's pretty straightforward. So I think you should get it. But if you still have confusion, please let me know in the comment section. Thank you. Let's look at the second one. Hydrogen and oxygen have oxidation number of +1 and -2. The iron has a charge of -1. So the sum of the oxidation number must be -1. Letting Y be the oxidation number of phosphorus. That means that -1 will be equal to Y plus 2 multiplied by +1. That's from hydrogen. And then +4 multiplied by -2 from oxygen. So when we do that, we end up having the oxidation state of phosphorus represented with Y to be what? +5. So it exists in the +5 oxidation state in that particular compound. Okay. Okay. So we move now and we talk about redox reactions as changes in oxidation number. Redox reactions as changes in oxidation number. Okay, so oxidation is an increase in oxidation number. So redox reaction as changes in oxidation number, we can easily say that when we talk about oxidation, it's an increase in what? In oxidation number. Reduction is a decrease in oxidation number. So we have established that. Now we give some examples to buttress that. When you have iron 2 proceeding to iron 3 plus 1 electron, what we have there is an increase in the oxidation number from +2 to +3. So that is an oxidation, is an oxidation. But when you have chlorine plus 2 electrons to give us Cl minus with a coefficient of 2, what we see there is a transition in oxidation number from chlorine at 0 to -2. So there's a decrease in the oxidation number. So a decrease in the oxidation number implies what? Reduction. Okay, all right now. So let's move it. Yeah, so this is another one. We have zinc plus 2H plus to give us zinc 2 plus H2. What we see is a transition in zinc from zinc 0 to zinc 2 plus, that's an increase in oxidation number. So that is oxidation. And then the converse we see in hydrogen moving from +2 to 0. So that's reduction. So that's redox reaction as changes in oxidation number. We can also have these two and break it down into oxidation and reduction. Okay, we can see aluminum transiting from 0 to +3. Okay, all right. So that's an oxidation. The reduction part is where we have the copper being reduced to from +2 to copper to 0, just elemental copper. So that's reduction. And then we can also have it with this particular example stated. We can see a -2 moving to 0. So that's an oxidation because it's an increment, it's an increment from negative to the positive side of the number. So it's a -2 to 0. That's an oxidation. What's it called? Okay, yeah, this one is a reduction from +2 to 0. So that's a reduction. That's good. Okay, so I believe we understand these as redox reaction as changes in oxidation numbers. So increment, decrease, and so on and so forth, and what it connotes. Okay, so we can move on now to other things and look at identifying redox reaction using oxidation number. How do we identify redox reaction using oxidation number? Like we said, a redox reaction involves a change in oxidation number of one or more atoms. A change in oxidation number of one or more atoms, okay? Now, we look at this example. We have ion 2 plus chlorine to give us ion 3 plus chloride ion in that regard. Now, when you look at it, Fe is oxidized. It is oxidized from +2 to +3. That's an increment in its oxidation state. So it's oxidized in that reaction. Chlorine, on the other hand, is reduced because it is moving from 0 to -1. So it's a reduction. It is being reduced. Okay. So I want you to try this on your own. I want you to tell me what the answer is by putting it in the comment section, and I will react to it adequately. Also, look at this particular one. Tell me which species is oxidized and by how much. What is the transition in the oxidation number? So please make sure you attempt this. And this is another one that I want you to attempt. And this is yet another one that I would like you to attempt. So please make sure that you engage this class activity, and you let me have the answer in the comment section so that I'll be able to tell you whether you are correct or you are wrong. Okay, thank you. All right, now let's move along quickly and look at balancing redox reactions using oxidation numbers. Balancing redox reaction using oxidation numbers. So for us to balance redox reactions using oxidation number, there are certain steps that we must follow. And the steps include, number one, you must first separate the equation into two half equations. One for oxidation and one for reduction. That's the first thing that you must do. So the second thing is that the equation is then balanced by adjusting coefficients and adding water, hydrogen ion, and electrons in this order. So that is how you go about balancing the redox equation. Under that one, you must understand that you balance the atom in the equation apart from oxygen and hydrogen. So you balance the atoms in the equation apart from oxygen. So you leave hydrogen and oxygen out initially. You leave them out, but you balance the atoms in the equation first. So you balance them by introducing coefficients, you understand? So just introduce coefficients to use to balance them. Then secondly, you balance the oxygen atom, then you add appropriate number of water molecule to the other side. So to balance, sorry, pardon me, please, to balance the oxygen atom, you will add the appropriate number of water molecules to the other side. So that's how we balance the oxygen, by introducing water. So that's very, very important. Okay. Also, to balance the hydrogen atoms, including those added in step 2, you add hydrogen ion, to the side that would need it in order for you to be able to get it balanced. You get. So that's very important. So these orders are very, very important that we should take note of them and we'll follow them strictly for us to be able to have a balanced redox reaction. We also add up the charges on each side, and that's more like going into the final stage now. You add up the charges on each side, they must be made equal by adding enough electrons to the more positive side. So that's that. So the next step that we need to also take note of is that the electrons on each side must be made equal. If they are not equal, they must be multiplied by appropriate integers to be made the same. Very, very important. The number of electrons that you have on the left-hand side must be equal to what you have on the right-hand side. Okay. All right, see this now. So the half equations are then added together, canceling out the electron to form one balanced equation. Cancel out as much as possible. So we don't include the electrons in it, we just cancel them out. So we just try as much as possible to ensure that the electrons are they are the same on both sides, and we just knock them out. And then we now bring the half equation of together, and then we form a balanced equation. If the equation is being balanced in a basic solution, the appropriate number of hydroxide ion must be added to turn the remaining hydrogen ion into water molecules. So we must also take note of these, and also the equation can now be checked to make sure that it is balanced. So you check it out in terms of atoms, in terms of electrons, in terms of all that you need to check. So just check it out like that to be sure that the equation is now balanced. Okay, I haven't gone through the steps, let's now try to attempt, a balancing a redox reaction. And this time around, we want to balance the redox reaction in an acidic medium, Okay, this is the equation that you have here. So the first thing is to go with the rule. They say we should separate them into two half equation. Read the oxidation half and then the reduction half. So steps to balance the equation. Number one, separate the half reactions that undergoes oxidation and reduction. That's the first thing. The second thing is okay, let's quickly do that first. So the iodine is moving and then giving us that's the oxidation part, because it's moving from -1 to 0. So the second one is that this is the oxidation half, because the oxidation state changes from -1 on the left side to 0 on the right. This indicates a gain in electrons. Okay. So we now look at the reduction part. We look at the reduction part now, and what is being reduced is the manganese. Oh, okay, so we have the manganese that is transiting from a negative, what's it called? This is the reduction half, because the oxidation state changes from +7 on the left side to +2 on the right side. This indicates a reduction in electrons. So that's the reduction. So we have done that now. The next thing to do is to proceed to the step 2, which is to balance this half reaction. We must first balance all the atoms except hydrogen and oxygen. So how do we go about this? Let's quickly look at it now. In terms of the oxidation, I want to balance in terms of the atoms now. So I need to introduce a coefficient of 2 behind the high minus, and then that balances this in terms of atoms. So in order to balance the oxidation half of the reaction, you must first add 2 in front of the iodine on the left-hand side. So there is an equal number of atoms on both sides. Okay, that's fantastic. We do the same thing for the reductions half of the equation too. So we do that, and we look at it for the reduction half of the reaction. You can notice that all atoms other than hydrogen and oxygen are already balanced, because there is one manganese atom on both sides of the half reaction. Okay, so having done this, the step number 3 that we need to follow is to balance the oxygen atoms by adding water to the side of the equation that needs oxygen. Okay, so we are going to do that, and when we do that, we'll end up having something like that. So once you have completed this step, add hydrogen to the side of the equation that lacks hydrogen necessary to be balanced. So we will do that, and then so because there are no oxygen or hydrogen atom in this half of the reaction, it is not required to perform any kind of balancing. So this one is good, it's fine. We move on. So the only way we want to balance this one is maybe we want to balance it in terms of maybe electron-wise now, which we are going to get to very soon. But the reduction half of the equation, you discover that you have oxygen, you have hydrogen, so you need to carry out step 3 on this particular one. So the first step in balancing this reduction using step 3 is to add 4 molecules of water atoms, 4 molecules of water, in order to balance the oxygen atoms with the 4 on the other side of what? MnO4 minus. So we do that. Once you add that, so the oxygen looks balanced or is balanced by so doing. the oxygen is balanced, okay? But we are not going to stop there. We are still going to push for that and look at it. And if you do that, that means we need to balance the hydrogen because we have now ended up increasing the number of hydrogen atoms. So we need to introduce a 8 hydrogen ions on the left-hand side of the equation. And that is exactly what I just said with this statement. Now that the oxygen atom have been balanced, you can see that there are 8 hydrogen atoms on the right-hand side of the equation and none on the left. And therefore, you must add 8 hydrogen ion atoms to the left side of the equation to make it balanced. So when you do that, you have done a very good work. So having done that, we're now going to the step 4. Now that the two half reactions have been balanced correctly, one must balance the charges in each half reaction so that both the reduction and oxidation halves of the reaction consume the same number of electrons. And the whole essence for doing this is because we want to cancel out the electrons. Okay, we want to take them out. So we are going to do that very, very shortly. So for the oxidation half, what do? We add 2 electrons to the iodine, elemental iodine that we have on the right-hand side. So when you do that, you have balanced it in terms of charge. So it's balanced in terms of atoms, it's balanced in terms of charge too. So, and that was exactly what this statement, and that's what the statement is actually explaining. So you have 2 electrons on both sides. So 2 minus 2 minus 2. Yeah, okay. So we now move to the reduction part now, and we try to do the same thing, introducing an electron that will make the left and the right hand side to become balanced. So if you look at it critically, you see that we have a total number of 7 electrons on the left hand side initially. That's ab initio. We have what? A total of 7 electrons on the left hand side, and then a total of 2 electrons on the right hand side. For us to balance it, what do? We add 5 electrons to the part that has more electrons, so it will reduce it, and then it will make what we have on the left-hand side to be equal to what we have on the right-hand side. Okay, all right, so that's what we're going to do. So when we do that, you discover that they will now have a balance how to look, they will have a balanced outlook, so that's just basically it. How did we get 7 electron on the left hand side? It's just by 8 minus 1, 8 electrons from 8 electrons from hydrogen, and then 1 electron from the manganese oxide ion that is there. So that's how we got that. So you just try to balance that by adding 5 electrons, and then you're good. You'll be fine. You'll be able to have 2 electrons on both sides of the equation. So that's what we just try to explain with all the statements here. Okay. So therefore, the overall charge of the right-hand side is +2. We must add 5 electrons to the left-hand side of the equation to make sure that both sides of the equation have equal charges of +2. Which we have done. Then we look at step 5. Step 5 says that multiply both sides of both reactions by the least common multiples that will allow the half reaction to have same number of electrons and cancel each other out. Now, if you look at it critically, we have 5 electrons in the reduction half cell, and then in the what's it called? Oxidation, we have 2 electrons. So we need to look for a way to balance this. So we need to introduce an integer that will enable us to be able to balance. Now, what do? The best we can do is to multiply the oxidation half by 5. So when you multiply the oxidation half by 5, what you end up having is 10 iodine ion, and then 5 iodine plus 10 electrons. And so we do that, then we do the same thing to the reduction. No, we don't do the same thing to the reduction. What we do to the reduction side is we multiply this one by 2. We multiply this one by 2. The whole essence of doing this is because we want to have the same number of electrons so that we can cancel the electrons out and then combine the equations together. And then we can have a balanced redox equation. So we multiply it by 2, and then we end up having 10 electrons plus 16 hydrogen ion plus 2 MnO4 minus, and then 2 Mn2 plus 8 H2O. All right. See, now if you look at this critically, you discover that for the oxidation and the reduction side, that there's there's a parity. That is, what I mean by parity is that there's an equalization in the number of electrons. The number of electrons is now 10, 10. So we can use that to cancel out, and thereafter just combine the equation. And then you have a balanced equation by so doing. So that is exactly what we did. And then we cancel out the number of electrons. And thereafter, we want to now look at step 6 that says that add the two half reaction to obtain the overall equation by canceling out the electrons and water and hydrogen ion that exist on both sides of the equation. Okay, so the overall equation will look like this: 10 iodine ion plus 16 hydrogen ion plus 2 MnO4 minus to give us 5 I2 plus 2 Mn2 plus H2, 8 H2O. Now, when you look at it critically, in terms of atoms, they are balanced. Both the left-hand side, what you have on the left-hand side is synonymous, is similar to what you have on the right-hand side. 10 iodine on the left-hand side, 10 iodine on the left on the right-hand side, 10 what's it called? I'm sorry, pardon me, 16 hydrogen on the left-hand side and 16 hydrogen on the right-hand side. We have 2 manganese on the left-hand side, 2 manganese on the right-hand side, and then we have 8 oxygens on the left-hand side and 8 oxygen on the right-hand side. Also, in terms of charges, you can also see that they are also balanced. How do I know that? Let's do it this way. 16 minus 10 will give us 6. 6 minus 2 will give us 4. 6 minus 2 will give us 4. That is the total number of electrons, or yes, electrons that we have, the total number of charges that we have on the left-hand side. If you look at the right-hand side, which is the product side, you can see that the total number of charges also is what? Is 4. 2 plus multiplied by 2, they will give us 4. So in terms of atoms and in terms of charges, they are balanced, so they are good. So once you arrive at this, you have balanced the Redox equation, and you can pat yourself on the back for a job well done. I hope you understand the concept. Pretty straightforward. All you need to do is to follow the rule closely, make sure you pay attention to the details, and you will find very simple. So we move on now. We look at balancing redox equation in basic medium. What we just did is balancing in acidic medium. Now, looking at it in basic medium, the balancing procedure in basic solution differs slightly because of what? OH minus, that's hydroxide ion, must be used instead of hydrogen ion when balancing hydrogen atom. To give the previous reaction under basic conditions, 16 hydroxide ion can be added to both sides on the left, and the hydroxide and the hydrogen ion will react to form water, which we cancel out with some of the water on the right. Okay, now, so when you look at it, let's break it into perspective now. You look at the equation. If it's been balanced on the, what's it called, in the basic medium, so what you have is that you have 16 hydrogen ion and then 16 hydroxyl ion. So it will cancel out in that manner. And then you have a 16 hydroxide ion still reflecting on the right-hand side. So on the left side, the hydroxide and the hydrogen ion will react to form water, which will cancel out with some of the water on the right. And that is how we do it when we balance in basic medium. So what you end up having will look like this. When 16 hydrogen ion and 16 hydroxide ion combine together, they will form water most definitely. And when they form water, there will be 16 molecules of water that will be formed. And if you look at it vis-a-vis what you have on the right-hand side, which is the product side, you discover that it's still the same thing that you have there. So that is how to know to balance. So he said 8 water molecules can cancel, leaving 8 on the reactant side, and that's true. So we can also still, what we are just saying that, okay, we can actually simplify further. Oh, we have arrived at the balanced equation, but let's simplify it a bit further. So we can cancel 8 water molecules, leaving 8 on the reactant side. Yeah, that's very, very correct. So when you do that, you end up having this particular equation as displayed on the screen. So this is the balance reaction in a basic solution. This is a balanced reaction in terms of atoms, in terms of charges, they're balanced. So that is how to balance in basic in basic medium. Thank you. I hope you understand the concept. Please, if you are not getting it or you did not get what I've explained so far, please do well to put your concern or your gray area that you don't really understand in the comment section. And then I will attend to it and try to provide a solution to whatever question you are posing. So I want to engage you. So with this class activity, I want you to balance this equation as seen on the screen. Please, everybody must engage with this question. Very, very important. The only way you can know whether you've gotten a concept is by attempting to what? To provide solution to a problem that is given after you have been taught the concept. So please ensure that you take it up and you're doing it. And when you get your answer, put it in the comment section, and then I will let you know if you're correct or otherwise. So please, these are the questions I want you to balance, and you're balancing this one in acidic medium. So please take note of these. You're also balancing the third one in acidic medium, but the fourth one, okay, the fourth one is also in acidic medium, but the fifth one, I want you to balance it in both acidic and basic environments, as in acidic and basic medium. So please make sure that you engage with these questions, and it will do you a whole lot of good if you can try it. You see your mistake, you learn from it, and get better at solving, problems like this. Okay, so please do them. Put your answers in the comment section, and you will get the appropriate reactions from me. Okay, moving along now to another thing. IUPAC nomenclature using oxidation number. How do we name, compounds using oxidation number? That is what IUPAC nomenclature using oxidation number connotes. Okay, the IUPAC, International Union of Pure and Applied Chemistry system, uses oxidation number in naming compounds. The sum of the oxidation number for a compound is 0. To name a compound, it can be done by adding the oxidation number of all the elements in a compound. So let's look at some of these examples and try to name some compounds now. This one says that calculate the oxidation number of the elements underlined and write the IUPAC name of the following. The underlying atom or element is sulfur in Na2SO4. So we need to calculate the oxidation number and then write the IUPAC name. The second question, the underlined is chlorine in potassium chlorate. So I'll mention the name. Okay, but I've not said the IUPAC name, so we can still calculate and then still get the IUPAC name. Okay, all right. Then CuNO3, and let's just go into it and let's provide solutions now. For the first one, the oxidation number of sulfur in Na2SO4. The first thing is that we'll make sulfur the unknown. So let X for xylophone. We'll use that to represent sulfur, and sodium is +1, oxygen is -2. We know that it's established. Okay, so let's bring it in. Na2SO4, when you add all the individual atoms, it will be equal to 0. And that was what we did here. And then when you do that, you can now look for the unknown, which is sulfur. So sulfur will be equal to what? 6, according to our calculation. So the oxidation number of sulfur in Na2SO4 is +6, So the IUPAC name, therefore, based on the oxidation number of sulfur that is +6, the IUPAC name of this compound would therefore be referred to as sodium tetraozosulfate 6. Sodium, Na, sulfur is sulfate 6. But before we get to sulfur, we need to mention the oxygen, which is 4 oxygen atom. That's why we said it is tetraozo. Ozo is representing oxygen. Tetra refers to 4. So sodium tetraozosulfate 6. The oxidation state of sulfur is 6. So we need to put that. So that's the IUPAC name. So very, very simple and straightforward. Understand it, apply the rules, and then you'll be fine. So I will solve the second one, but I'm not going to solve the third one for you. So get ready to solve the third one yourself. Okay, let's look at the second one. Chlorine in KClO3. Okay, so our Y will be used to represent our chlorine, which is unknown. Potassium is +1, and oxygen is -2. Okay, so if you sum off the individual atoms in potassium, in KClO3, it will be equal to 0 based on our rule. So when you apply, you have your chlorine to be plus 5. So the oxidation number of chlorine in KClO3 is plus 5. So based on that, we can actually give the IUPAC name. The IUPAC name for this compound would therefore be potassium trioxo chlorate 5. Potassium trioxo chlorate 5. That's very good. So based on the oxidation number, we've been able to determine what the chlorine is in that particular compound. Okay. So this one, I want you to do it yourself and let me know what you come up with after you have solved it. Okay, let's move on now. We want to test, how do we test for oxidizing and reducing agents? For us to test, start off with the test for oxidizing agents. The first way or the first method is the use of iron 2 chloride. The solution of this substance, iron 2, is green in color. So when reacted with a substance suspected to be an oxidizing agent, its color will change to what? Reddish brown. Then the substance is confirmed to be an oxidizing agent. And why is that? It's because the iron 2 ion is oxidized to what? Iron 3 ion. So that is what happens there. So we can use iron 2 chloride to test for oxidizing agent. The second method is when we use a strip of moist starch iodide paper. When you use this a strip of moist starch iodide paper, you dip it into a substance suspected to be an oxidizing agent, and a blue-black color appears, then the substance is confirmed to be what? An oxidizing agent. So that's the second method. So oxidizing agent oxidizes the iodide to free iodine. The solution of the free iodine then reacts with the starch to give the blue-black color. Notice that it is only the solution of the free iodine that gives the blue-black color with the starch. Okay, so please, this is how we test for oxidizing agent. Now, moving along now, okay, there's a third method, pardon me, please. There's a third method, and that is the use of hydrogen sulfide. Hydrogen sulfide is reacted with a substance and some yellow deposit, and that deposit is just a deposit of sulfur, are settled on the bottom of the container. Then the substance is an oxidizing agent. That is, H2S is oxidized to sulfur. So when you test and you test with H2S and you discover yellow deposits, that deposit is sulfur. So that shows that that substance that you have tested H2S against is actually an oxidizing agent. Okay, let's talk about reducing agents now. To test for reducing agents, we can use this first method. Reacting the suspected reducing agent with potassium tetraoxomanganate 7 solution. That's KMNO4. It's a mouthful. Okay, so we test with KMNO4. KMNO4 is traditionally purple in color. And then when you test with any substance that is a reducing agent with KMNO4, the color that is observed is that it will become colorless, which is as a result of a reduction of KMNO4 to manganese 2+. So the substance is confirmed to be a reducing agent. KMNO4 is reduced to Mn2+. So when the purple color changes and becomes colorless, then that substance is a reducing agent. Okay. The second method that we can use to test for reducing agents is to use a solution of potassium heptaoxo dichromate 6. Potassium heptaoxo dichromate 6. Okay, it is naturally orange in color. But when you add a reducing agent to it, it will become green. And this is because the K2CR2O7 has become reduced to what? Chromium 3+. When a reducing agent is added to it. So these are ways in which we test for oxidizing and reducing agents. So please, let's take note of it. It's very, very important. And it will bring us to the end, to the summary of the class. We'll be summarizing. So we'll be doing a summary of the whole lesson on oxidation and reduction. And we have talked about redox reaction, which involves the transfer of electrons between substances. We've also talked about oxidation as being the loss of electron, while reduction is the gain of electron. We've established that oxidation can also be defined as addition of oxygen and removal of hydrogen. So we've established this in the course of the lesson. And we also talked about the fact that oxidation numbers help identify redox changes in chemical equation. And then a redox reaction always include both an oxidizing agent and then a reducing agent. So we've talked about these and we've looked at the application of redox or redox reaction in basic life functions, like photosynthesis, respiration, combustion, and corrosion. And then we've looked at how to balance redox equation both in basic and acidic medium, and then how to test for reducing and oxidizing agents, and how to naming using oxidation number. So we have looked at this in the course of our lesson. So please, if you have any area that you're not so, yeah, you are still confused, please let me know in the comment section. Yeah, thank you. So let's quickly evaluate this class, and I will evaluate with the following question. Which of the following best describes oxidation in terms of electron? Is it gain of electron? Is it loss of electron? Is it sharing of electrons? No change in electrons. So please let me know what you feel in the comment section. That is the answer. In the reaction Na and Na to give us Na plus electron, which process is taking place? So tell us, is it reduction? Is it neutralization? Is it oxidation or combustion? What does the acronym HOIRIG stand for? So you tell me in the comment section, pick an option and let me know if you still remember that acronym or that mnemonic that I taught you in the course of the lesson. Also, which species is reduced in the reaction? So look at that reaction closely and tell me which one is being reduced in that reaction. Okay, so pick the right option. And okay, so all right. So look at this ones too and let me know what you feel the answer is. Okay. All right. So look at them carefully and let me know what's your answer are in the comment section. Okay. As we are trying to bring this lesson to a close now. So, okay. So please look at it. Let me know what the answer is. Okay. So please, you have to get a pen and a paper for the last one. So work it out and let me know. Okay. Thank you. And with that, we've come to the end of the lesson, and I hope you got something significant from the lesson today. Please, I want you to tell me if you have any challenge in anything I've discussed. Just put them in the comment section, and then I will do the needful to it. Thank you for joining in this lesson. I will see you in the next video.